Okay, let's unpack this. We talk a lot about power, in terms of amplification. So just think about your own physical strengths for a second. You, as a person, you can exert, what, maybe a few hundred pounds of force, just raw biological power, but then you step into an excavator or you stand behind some massive factory press. Suddenly, that raw input is multiplied by, I don't know, a factor of hundreds, thousands even. You don't actually get stronger, you're just controlling a system that's exponentially more powerful.
Precisely. And that's the crucial distinction Lem makes right from the get-go. The human is the regulator, the controller. You provide the intention, the fine-tuning.
Yeah.
But the machine itself is the overwhelming source of that amplified energy.
Right, it's an external boost.
Exactly.
So, okay, now stop thinking about physical strength and start thinking about the mind. What if we could apply that same enormous factor of amplification to human intellect? I mean, not just making us think a little bit faster or giving us, better search tools, but truly making us capable of solving problems that are, frankly, way beyond our collective grasp right now. And that is the core question for us today. Stanislav Lem's revolutionary idea of the intelligence amplifier.
We are diving deep into some foundational stuff here. It's philosophical futurology, it's cybernetics, and we're drawing directly from excerpts of Lem's seminal 1964 work, Summa Technologiae, specifically Chapter 4, which he called Intellectronics. And this text is so foundational because, this is decades before AI was a household term. Lem was already grappling with the engineering limits of creating, a truly superhuman intelligence.
And his starting point, it isn't about predicting gadgets or, the next cool tech. It's a really profound point about the limits of our own methods.
He sees this relentless advance of science, what he calls the general tendency of mathematization.
This drive to just apply mathematical rigor to every single field you can think of.
To everything. The idea that everything can be boiled down to a system of equations.
Yeah.
And then that entire system just hits a wall. And that realization that the very bedrock of science, mathematics, suddenly wasn't enough for certain advanced goals. That's really the engine of the whole book.
And that's our mission for you, the listener. In this deep dive, we're going to explore why traditional math, the backbone of all modern engineering, just suddenly proves insufficient for what Lem wanted to do. We'll look at how he proposes to build a machine that is demonstrably smarter than its own inventor.
Which is a paradox in itself.
A total paradox. And he does it using this radical black box approach. And we'll explore what that really implies for the future of how we build things.
It's a complete paradigm shift. It's moving from engineering what you know to deliberately creating what you do not yet understand.
Okay, so let's start by just establishing how widespread this mathematization trend really was when Lem was writing. He wasn't exaggerating this at all. Historically, math was for physics, maybe a little chemistry.
Right.
But Lem sees it starting to spread, everywhere.
Oh, absolutely. He saw this huge intellectual land grab, fields that were always qualitative, not quantitative.
Yeah.
Biology, psychology, medicine, they were all being increasingly quantified.
With what? Statistical models and things like that?
Exactly. Statistical models, information theory, systems analysis. It was like this massive and very successful colonial venture by mathematics into the softer sciences.
And he details these specific, almost comical, he calls them partisan raids into the humanities. This idea of taking these really abstract human things and trying to just force them into a formal mathematical box.
Yeah, the source specifically brings up theoretical linguistics, trying to formalize the deep, messy structures of language with mathematical logic. That was a big research area then. But the one that really stands out is applying information theory to literature.
For literature.
Yeah, trying to quantify literary and especially poetic texts.
Wow. Okay, just stop and think about that for a second. You're trying to use statistical rigor like entropy and information density to measure the aesthetic value of a sonnet or a haiku?
It just shows you the mindset at the time. It was maximalist. The belief was that if a thing exists, if it carries information, then it must be quantifiable.
And therefore you can master it.
And therefore you can master it theoretically.
Yeah.
Science had become so powerful, it thought it could, define beauty with algebra.
But then, boom, the hard stop. You'd think if math can handle poetry, it can solve anything. But Lem says no. This unexpected solid wall just appears, and it forces engineers and theorists to admit the impotence of mathematics.
And this is where the real tension is. The problem wasn't that the equations were too hard. The problem was that mathematics itself, any kind of math, even brand new cutting-edge stuff, was just insufficient for solving problems in these new advanced fields of cybernetics.
So it's not like, oh, we just need to discover a new theorem.
No, it's a fundamental failure of the entire methodology.
And what are the subjects that are causing this huge intellectual roadblock?
They're all related to creating systems that can manage complexity on their own terms, not just systems that execute human instructions.
Right.
The issues all center on self-organizing homeostatic systems. And that's a critical term. We really need to unpack what Lem means by that.
Okay, so let's do that. What exactly is a self-organizing homeostatic system in this context?
Okay, so at its core, a homeostatic system is just one designed to maintain stability or equilibrium, even when external things change.
Like a thermostat in your house.
It's exactly like a thermostat, but, infinitely more complex. The self-organizing part means the system can actually change its own internal structure. It can invent new rules for itself in response to what's happening in the environment.
Without being explicitly programmed to do that.
Right. It adapts, it learns, it optimizes its own structure.
So we're talking about systems with these complex feedback loops that don't just regulate what comes in, but they dynamically restructure themselves to meet the goal. And that complexity, that's why traditional sequential math fails. You can't write an equation for every possible way it could rebuild itself.
You can't. The system has to adapt to unpredictable, non-linear events. And Lem identified three sort of high-level problems where specialists first really ran into this mathematical wall, this difficulty in modeling systems that could just spontaneously invent their own structure.
Okay, let's list them, because they really define the edge of what people were thinking in the mid-20th century. This is the point where traditional engineering ended and, I guess, futurology began.
So the first one, and it's our main topic, is the construction of an intelligence amplifier, a device that has to, by its very definition, possess intellectual capabilities that far exceed its creator.
Okay, one second.
Second is the creation of a self-programming automaton for production control. He called this the homeostatic brain of an automatic factory.
And that was the immediate practical goal of the day.
Oh, absolutely. An industrial brain that could manage and optimize these complex, changing supply chains and factory operations without needing a human to constantly reprogram it.
So think of a factory that doesn't just build cars, but it can instantaneously re-engineer its entire production line if a key part supplier fails.
Or if demand suddenly triples for one specific model,
Yeah.
that requires self-organization on a massive scale.
And then the third of the most general ultimate challenge.
Right, that's building a universal homeostat.
Which is what exactly?
It's the abstract idea of a truly generalized, self-stabilizing, self-organizing system, one that's capable of adapting across completely different environments and goals, from, climate control on a space station to planetary engineering.
So that's the trinity of problems.
That's it. And even though the factory automaton was the immediate priority, that's the one that would make the most money right away. The intelligence amplifier, or the IA, that's the one that gives us the clearest picture of the core philosophical and engineering difficulty.
Why is the IA more philosophically challenging than the factory brain? They both need self-organization.
Because the factory brain, as complex as it is, it's still dealing with physical constraints.
Right.
Industrial logic. You can still measure its success in tangible metrics, throughput, cost, efficiency.
Right.
But the IA forces the constructor to confront the absolute limits of their own cognition.
It's a machine that's designed to generate knowledge that the inventor cannot possibly possess yet. So, if the mathematics that got us to the moon and started analyzing poetry suddenly fails when it's faced with this need for self-organization, we need a completely new way to define the problem.
A new way to define the problem and the goal.
Let's look closer at the sheer scale of that goal. We started with the physical analogy, the excavator, and Lem really insists that the intelligence amplifier has to be its precise analog in the world of mental activity. It's the intellectual equivalent of a crane.
It's a very clean metaphor. Just like a physical power amplifier handles the heavy lifting, the IA has to handle the heavy intellectual load. And as we said, the human is only connected as a regulator, a controller, never the primary source of the intellectual horsepower.
So the human provides the goal, you define the problem, and the machine gives you the amplified cognitive thrust to solve it.
Right.
And to really get why Lem needed such a radical approach, we have to look at the numbers he uses. He actually tries to quantify what he's trying to amplify.
He does, yeah. He grounds it in the psychological data that was available at the time. He uses the IQ index to define the boundaries of, natural human intellect. So according to the tests back then, the average IQ is around 100 to 110.
And Lem is pretty clear about the biological ceiling, right? Even for the greatest thinkers.
He is. He says individuals with very strong natural intelligence, the people we consider geniuses, they might get an index of 140, maybe 1 in 50.
Hmm.
And the absolute upper, rarely reached natural boundary for human intellect is somewhere around 180 to 190.
So that's the limit.
That is the maximum complexity and speed that our biological neural networks can sustain, period.
So, okay, we have a scale that peaks naturally around 190. That's the limit of human intellectual horsepower. But if we want this IA to be like a factory machine, a machine that multiplies human strength by a factor of, say, 50 or 100, we need a massive jump.
Has to be an enormous multiplicative factor. Lem argues the IA needs an amplification coefficient that's comparable to a physical power amplifier.
So it can't just be an incremental boost.
No, not at all.
So how does that actually translate into the intellectual index? We're not talking about a 200 IQ here, are we? We're talking something on a totally different scale.
We are. The required amplification would result in an intellectuality index of around 10,000.
Yeah.
Or higher.
10,000.
10,000. And that number, that's the conceptual leap.
Right.
It means the system has to be able to grapple with problems that are hundreds of times more complex than those solved by a natural genius.
And that distinction is so key because it explains why a simple supercomputer wasn't what Lem was talking about. A supercomputer might solve a 190-level problem in milliseconds instead of years, but it's still just running a known, defined algorithm.
Exactly.
A 10,000 IA that has to be able to solve problems that the 100-level mind doesn't even know how to begin to approach.
That's it, exactly. The shift isn't speed, it's conceptual depth. So if a 190 IQ person can define the variables for a problem with 10 complex interrelated systems, a 10,000 IA has to be able to tackle problems involving thousands or even tens of thousands of those systems all at once.
Systems that interact in nonlinear ways that you can't just model step by step.
Exactly.
And the sheer magnitude of this is highlighted in the editorial notes.
Mm-hmm.
We're told that a person armed with this device would be able to solve as many problems as 100 ordinary, unequipped people.
It's an exponential increase in your problem-solving bandwidth. It makes the human operator into a kind of conceptual demigod.
And it fundamentally changes the relationship between the human and the task. You move from being the main calculator to being the high-level architect. You provide the direction, and the IA does all the heavy, multi-layered, nonlinear lifting.
But this is precisely where the paradox of creation just slams the door shut on traditional engineering.
Okay, here's where the engineering problem meets philosophy, and it gets truly mind-bending. The core difficulty of building this thing is this fundamental paradox of creation.
The difficulty is irreducible, and you can state it very simply. The constructor must create a device that is, by definition, smarter than himself. The intelligence amplifier has to be capable of intellectual feats that the person building it cannot fully conceive of, let alone perform.
But wait a minute, is that really a paradox? Or is it just a massive challenge? I mean, don't we build things smarter than ourselves all the time? We build bridges that can withstand stresses no human could calculate in their head?
That's a great question, and it gets right to the heart of Lem's argument against traditional cybernetics. When we build a bridge, the engineer fully understands the theory. They know Newtonian physics, material science, structural load calculations.
Okay.
The computer just runs the calculations faster. But the output is completely bounded by the known theory.
But the IA's required output, that 10,000 index that demands new theory.
Precisely. If the inventor could solve the 10,000 level problems, they wouldn't need the machine in the first place. But since they can only think at, let's say, 180, they have to figure out how to create a machine that operates at 10,000.
It's a conceptual impossibility.
It is, if you rely on defining the solution before you build it.
So, okay, let's talk about the failure of traditional programming then, in light of this paradox. What happens if the constructor sticks to the standard method? You know, developing a detailed, pre-existing program for the machine.
If they do that, the goal is fundamentally blocked. The traditional method requires the constructor to write out a detailed, structured sequence of logical operations. But that pre-existing program, it places an absolute fixed limit on the machine's intellectuality.
And that limit can't be higher than the mind of the person who wrote the code.
It cannot surpass the cognitive horizon of the creator.
I see. It's like asking a programmer who only knows basic arithmetic to write a program that will spontaneously invent calculus.
That's a perfect analogy.
The program can run the arithmetic operations at lightning speed, but because the structure of calculus isn't in the programmer's conceptual toolkit, it can never, ever appear in the machine's output.
You've amplified the speed, but the conceptual depth is hard-capped.
The machine can only execute what the mind that built it could conceive of.
Exactly. It can run the known algorithm faster,
Yeah.
but it can't develop a truly novel, nonlinear, self-referential algorithm that the human programmer couldn't have at least mentally simulated.
And this realization leads directly to the impossibility of prior theory.
Yes. Lem states that the problem becomes insoluble if we insist on creating a complete theory, a necessary mathematical theory, before we build the amplifier. The requirement is just paralyzing. We have to formalize the theory of how to be exponentially smarter than ourselves before we build a machine that will demonstrate that smarter behavior.
It makes no sense.
It doesn't.
And this is where Lem brings in his famous analogy just to show how completely futile this traditional approach is.
It's the ultimate intellectual exercise in futility. He says it's like proposing to lift oneself by one's hair,
Okay.
especially when you're carrying a 100-ton load tied to your feet.
Right. It's physically, logically, and mathematically impossible under the current rules.
It's impossible. The 100-ton load is the overwhelming complexity needed for 10,000 level intelligence.
And the method, trying to create the formal theory first, is the intellectual equivalent of pulling on your own hair.
It's a self-defeating endeavor. The theory you need only exists after the goal is achieved.
So the paradox demands a radical solution.
A completely radical solution. If you cannot create the theory first, you have to abandon the need to understand the internal process before you build it. You have to leap and just trust that the result will validate the process.
You have to embrace engineering heresy. So this hypothetical new approach that Lem suggests, it completely upends the philosophy of engineering. It means we have to accept that detailed knowledge of the internal structure of the device is not just unnecessary, but it might actually get in the way of the goal.
This is a radical break from, the entire Cartesian tradition of science. For a traditional engineer, understanding every single component, every connection, every state transition, that's the very definition of competence and control. And Lem says, no. We have to willingly become ignorant of the intermediate steps and just embrace the black box.
So let's define that clearly. A black box here isn't just, a component we don't understand that we assume works.
No.
It's a device whose internal structure and sequential states are considered completely fundamentally unknown to us because that structure is nonlinear, it's adaptive, and it's just too complex for our 190 IQ minds to model mathematically.
So the focus shifts entirely from internal analysis to external pragmatism. We are not interested in how the amplifier gets to its conclusions. We don't care about its internal wiring or its specific algorithms. The only point of interest has to be the final, verifiable results of its action. Does it solve the problem, yes or no?
It's the ultimate results-oriented philosophy. And Lem asks this really striking question. What does the internal complexity matter if the device truly behaves like an intellect with an index of 10,000? I mean, if the output is a successful solution to a previously unsolvable problem, then the internal design, however incomprehensible it is, must be correct.
The proof is in the pudding.
Exactly.
It's a move toward engineering by emergence rather than engineering by design. You create the conditions for complexity to organize itself toward a goal, rather than meticulously scripting every single step of that organization.
To make this abstract idea more concrete, Lem provides this fantastic, illustrative, and honestly, pretty strange experiment.
The infusoria magnetic homeostat.
Yeah! You really have to admire the way he used biology to illustrate the future of cybernetics.
It's a truly crucial detail because it shows that controlled complexity can be harnessed without actually being understood.
Okay, so let's break down this bizarre setup.
All right, step one. You start with a colony of infusoria.
These are tiny, single-celled organisms, right? Protozoa in a little aquarium.
Exactly, and the complexity of even one of these organisms, its internal biochemistry, is far beyond what we could draw in a schematic.
Okay, then you add iron powder to the water.
Right, and in this biological twist, the infusoria ingest tiny amounts of this iron along with their food.
And now comes the control element.
Now comes the control. The researchers creates an external, controlled magnetic field outside the aquarium. And this field is calibrated to influence the movement and the collective behavior of the whole iron-laden infusoria colony.
So the system is now defined. The input is the changes in the magnetic field.
The external measurable signals, yeah.
And the output is just the observable collective behavior of the infusoria, how they move around, the patterns they make.
Precisely.
And this is the critical point. The researcher has no idea about the biochemistry of the infusoria, or the specific cell mechanism that makes the iron affect its movement, or how the magnetic field translates into a neural impulse in a protozoa. They don't have the schematic.
Not at all. Even though the operational complexity of a single infusory is completely unknown to us, and we definitely can't draw its functional diagram, we have successfully created a controlled whole, a systemic unity.
A system that exhibits behavior governed by external signals.
Yes, we achieved a functional result, a controlled reaction to an input signal that emerges from elements whose complexity remains fundamentally incomprehensible to the designer.
So the theoretical point stands. You can successfully build and control a functioning, self-organizing system using elements whose detailed internal operation is totally opaque.
You don't need to model the individual protozoan. You only need the collective systemic outcome, the functional black box.
And this is why Lem's methodology was considered heresy.
Oh, absolutely.
This search for new building materials, especially ones that were almost like living systems, colloids, multi-component solutions.
They were looking for positive feedback effects in materials, for systemic complexity to just emerge naturally rather than being forced by pre-written code.
And you can see why traditional engineers trained to calculate stress limits and electrical resistance would just see this as witchcraft.
Of course, it meant admitting that the most advanced technology might be fundamentally non-transparent, that it relies on emergent properties rather than explicit design.
The opposition was natural because it threatened the very idea of scientific mastery.
Right. If you can't fully understand it, can you truly control it?
And Lem's answer is, you can control the input and the output. And in the case of the IA, that pragmatic control is all that matters.
So we are moving from being meticulous watchmakers to being gardeners.
Gardeners?
Yeah, we plant the seeds and we trust the complex genetic code that we can't fully read to grow something spectacular.
Which brings us to the ultimate philosophical payoff. The nature of calculation itself.
So regardless of whether those infusory experiments were actually useful, the principle forces this principled shift in engineering methodology. You move from trying to calculate everything a priori to just accepting success based entirely on the results.
And this creates a really clear contrast between the old engineer and this new heretical cyberneticist. The old engineer relies on conscious, formalized theory. The heretical cyberneticist relies on realized, flawless action.
Let's use the jumper analogy. It's one of the most powerful concepts in Summa technology. Imagine a person standing on the edge of a ditch they need to jump across. The old engineer approaches this problem by trying to calculate every single variable before the action.
They would need to formalize the entire physical and physiological system before the jump is even made, right? I mean, that calculation would be staggering.
Absolutely staggering. They would need to quantify the precise force of gravity at that exact latitude and altitude.
All right.
They need to calculate the contractile force of every major muscle group involved, the biomechanical leverage of the bone structure, the kinematics of the body's center of mass.
And most complexly, the exact moment-to-moment neurological processes happening in the cerebellum, the part of the brain that's responsible for timing and motor control.
I mean, everything. They're trying to write down the entire textbook of physics and biology for one 3-second action.
That's the traditional model. You formalize the entire system before you do anything.
Meanwhile, the heretical cyberneticist Lem's new school, he just intends to jump over the ditch.
And if he successfully lands on the other side,
the problem is solved. The necessary physics has been flawlessly executed. The success of the act is the proof of the theory's realization.
But the philosophical question is, how can the jumper succeed without ever having written down a single equation? The person who jumps flawlessly probably got a C in high school physics.
And this is the profound concept of the brain's innate mathematics. Every single preparatory and realization step required for that jump, the perfectly timed sequence of muscle firings, the instantaneous calculation of force and trajectory, all of that is fundamentally a complex, incredibly convoluted sequence of mathematical processes performed by the neuronal network.
So the brain is running the equations, but the jumper is completely unconscious of the symbolic math.
Exactly. All the work within the neuronal network, the pattern recognition, the firing of synapses, the instantaneous adjustments, it is all mathematically equivalent to solving the differential equations of motion. It is what Lem calls the mosaic mathematics of the brain.
But the jumper, the person executing this perfectly, is completely incapable of writing down the rigorous theoretical mathematical equivalent on paper.
Can't do it. They cannot provide the formulas that their own neural network just executed perfectly.
So this introduces the concept of biomathematics, this innate mathematics that's practiced by all living organisms, all the way down to the infusoria we were just talking about.
Yes, it's a system that solves problems perfectly, immediately, and implicitly.
And this innate system, it operates seamlessly inside the organism, constantly solving these high-level problems like equilibrium, energy conservation, motion control.
But here's the critical distinction. To translate this innate system into classical, verbalized, formal mathematics, the kind you're taught in school or university, that requires a slow, sequential, and often imperfect translation across completely distinct neurological systems.
You mean the act of formalization itself? The conscious writing of symbols, the structuring of logical steps, creating a written theory that's done by a separate part of the brain entirely.
A completely separate part.
Separate from the part that actually executed the jump.
Precisely. Formalization is a secondary cognitive function. It requires taking the instantaneous, holistic, massively parallel calculation of the cerebellum and forcing it into a slow, sequential, symbolic language.
The formal language is just a verbalized representation of a process that the brain already did instantly and perfectly.
Exactly.
So the intelligence amplifier's true function, then, must be to act like the flawless, nonverbal, implicit part of the brain, the part that jumps, not the part that writes the textbook explanation for the jump.
Yes. The solution lies in making sure the intelligence amplifier avoids the need for formalization, verbalization, and conscious construction. It has to function just as automatically, naively, skillfully, and flawlessly as the jumper's neural structures.
It's a machine that doesn't need to generate a 500-page report explaining why it found the solution. It just generates the solution itself. And the internal calculation happens in an instantaneous black box way.
Its sole job is pure signal transformation, accepting the complex human-defined input, the problem, and producing the desired output, the 10,000-level solution.
Which leads us to the ultimate and almost terrifying conclusion about the intelligence amplifier, and really about the future of any technology that relies on this kind of complexity.
The conclusion is this. Neither the amplifier itself, nor its constructor, or any external observer armed only with traditional mathematics will ever fully understand how the amplifier performs its task. But the singular defining requirement will be met. The desired, verifiable, successful results will be achieved.
We'll have the solution. And that pragmatic validation is the only metric that matters.
We will have successfully created a technology that is simultaneously perfect in its function and incomprehensible in its operation.
A profound trust placed in emergent, self-organizing complexity.
And that is the true revolution Lem foresaw. The end of engineering that's predicated on full knowledge. #tag OUTRO.
So when you boil it all down, what have we learned here? For you, the listener, I think the key takeaway is that Stanislav Lem mapped out a path for technology that accepts and even exploits the fundamental limits of human formal knowledge.
We started by recognizing the failure of formal math when it was confronted with these self-organizing systems.
Yeah.
This intellectual wall that engineers hit when they tried to build complexity that could adapt and organize itself.
Then we understood that core engineering paradox. That creating a system that's truly smarter than its creator is just impossible if the creator insists on defining the machine's full operational theory a priori.
You can't write the theory for something you haven't even conceived of yet.
And the revolutionary leap was the acceptance of the black box methodology, abandoning the need for internal knowledge and relying purely on external, verifiable results.
Yeah. We saw that validated by that strange but insightful example of the infusoria magnetic homeostat. It proved that control and utility can emerge from components you don't understand at all.
And finally, the fundamental philosophical shift came from recognizing biomathematics, this innate, flawless, nonverbal math that's performed by all living systems, from the lowest organisms to the highest functioning human brain.
And the intelligence amplifier has to mimic that silent, perfect realization of complexity, bypassing the slow sequential process of conscious, written formalization.
The ultimate shift for science is from understanding a process before you implement it to simply creating a successful result. And you only attempt to reverse engineer the understanding later.
Or maybe centuries later.
Or maybe never at all. We move from the scientist as master planner to the scientist as systems cultivator.
You know, the whole discussion about the biomathematics that operates flawlessly in the living world, it raises a really important final question for you to mull over. If our own brains perform these incredibly complex, perfect calculations automatically without our conscious ability to verbalize them. If the act of jumping requires non-conscious perfection, what percentage of intelligence have we truly managed to capture and formalize in our textbooks and our programs?
Lem's entire framework suggests that conscious, verbal knowledge, the stuff we can write down and teach in a classroom, that might only be the very tip of the intellectual iceberg. So is the future of technology fundamentally about bypassing our conscious, formalized processes to tap directly into that natural systemic complexity. If we can build a black box that thinks at 10,000, what happens when we start treating our own brains as black boxes we simply regulate?
The possibility is that the most powerful algorithms were always running inside us, and the intelligence amplifier simply provides the necessary system architecture to externalize that inherent nonverbal genius.
Until next time, keep thinking about the ditch you're trying to jump and whether you need to write the equations or just trust the magnificent, silent biomathematics of the jump itself.